So we're basically going to be talking about metrics, and the concept of metrics is kind of mixed in the sense where in the United States we don't really use metric system. We pretty much use the American standard or the English units, and so metrics is mostly used in a scientific kind of a setting where scientists in the lab, whether it's in the United States or whether it's in Europe or Africa, will be able to have a better sense of how to actually get information across without being confused with the units of measure. So metric units is basically what we're trying to do in order for us to try to get across the information in terms of a measurement. So there are some basic metric units. Um, we're going to be taking into the account of temperature when we get to thermodynamics. Time, we will be actually getting into that very soon. Length, which is a unit of measure for how long something is. Mass is how much stuff something has. Light intensity, very little. Amount of substance is in chemistry. Electric current, which we will actually be doing quite a bit in the second semesters. And so metric-based units is essentially kind of based upon these units. Now, the idea of units is mostly utilized in making or giving a value to a particular measurement. So, for an example, if you have a number 5, just by looking at the number 5, you know there's a quantity of 5, but we really don't have an idea 5 what. So it could be 5 apples, it could be 5 inches, it could be 5 miles. That 5 becomes kind of arbitrary if we were to put in the concept of units. So the units give sort of a value to a particular measurement. So for the purpose of the class, we'll actually be utilizing temperature, time, length, mass to some degree, yeah, actually quite a bit, light intensity, very little, amount of substance, almost not at all, and electric current. Now, any other units that you're going to be utilizing in class, like meters per second, is essentially not a base unit, but rather a derived unit. So a derived unit would be units that are utilized in a measurement that comes from two or more other base units. So if you look over here, A is the symbol for electric current. K is a symbol, capital K, stands for Kelvin, is a temperature unit. Again, A stands for ampere, K for Kelvin for temperature, S seconds for time, M is meters for length, kg, a lot of different sources would use kilogram as a unit of measure for mass, but I prefer to use gram since gram is a base unit and kilogram, this kilo right there is really just a prefix for that metric unit. CD is for light intensity, and that goes with the concept of candela, which we can talk about later if you want to ask a question or something like that. And MOL stands for mole. Now this, and that's for the amount of substance. Now SI is the system, an international system for measurement, and it's actually in French, which I can't pronounce, so let's kind of leave it at that. Now, for every single unit, to give the unit a little bit more, I guess, more value or more distinction or a better way to categorize it, we have metric prefixes. And just like in English, a prefix is a term of a part of a word that goes in front of another word. In this case, in front, this prefix will go in front of the SI unit, the metric units. So because each SI prefix has a predetermined value, a numerical value, it will change the value of that metric unit by a certain amount, thereby changing the value of that SI unit. So I'm sure in a lot of popular movies you have seen the word or heard of the word kilo. And the word kilo is essentially a synonym for 1,000. So kilo and 1,000 is the same thing. So if I were to say a kilo of something, I mean 1,000 units of that one thing. Now, meter by itself is basically has a value of 1. So if you put a kilometer together and to make a new word, we get a kilometer. And what that ultimately means is 1 kilometer has a value of 1,000 meters. Because kilo means 1,000, meter mean meters, so you got 1,000 meters. So you can affix prefixes to many different base units. Now here we have this big giant table, which is kind of over the top. And I'm not going to hold you accountable for more than, I guess from giga, which is 10 to the 9, or 1.0 times 10 to the ninth, to nano, which is 1.0 times 10 to the negative 9. Anything above and beyond those, well, it's okay to learn it if you want to, but I'm not going to hold you accountable for in terms of knowing what these values are. So the factor is basically exponential factor, 10 to the power of positive 9 for nano, positive 6 for mega, positive 3 for kilo, positive 2 for hecto, positive 1 for deca. And then you have, of course, where it says 10 to the 0, which has a value of 1. That is essentially the value for meters, liters, seconds, so on and so forth, the base SI base units. Then you have the 10 to the negative 1, which is deci, 10 to the negative 2, which is centi, 10 to the negative 3, which is milli, 10 to the negative 6, which is micro, 10 to the negative 9 would be nano. So I'll just hold you accountable from positive 9 exponents to negative 9 of the exponents. Of course, you need to know what it is in numerical value, right in here, the exponential value, which is over here, as well as the SI prefix, okay, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, and nano. And you need to know what these symbols are. And remember, when you look at this, there are upper and lower cases. Big G for giga, big M for mega, little k for kilo, little h for hecto, dA, both lowercase, for deca, little d for deci, little c for centi, little m for milli, and a Greek symbol called mu, which is like a U with a little whisker in front. Partly M, partly U, it's called mu, and that's a micro, and n, lowercase, for nano. So the unit conversions will allow us to change the values of the units with different prefixes, because sometimes you might get confused if you have a measurement that is a certain number of milliliters to some numbers in mil or centiliters, and because those two have different units, the amount of liquid in milliliters could be different than the amount of liquid in centiliters. So we want to have a way to convert the units from different measurements with different units to a common unit, which will make it easier for us to calculate numbers. So since the metric prefixes are based on the powers of 10, and the decimal systems are also based on the powers of 10, we essentially would like to use decimal values so that we are able to move the decimal point to the left or to the right to increase the value or decrease the value by a factor of 10 times, which is basically what we mean by the powers of 10 for the metrics prefixes. So in order for us to convert our units in metrics, we just simply have to move the decimal point to the left or to the right. Now the trick is to kind of know which way to move the decimal values. So that's kind of where our practice has to come in. So now here are some practice problems, okay, just to kind of get you up to speed in terms of where you want to be in order for you to be ready for the quiz this Friday. What is the symbol for the base unit that measures temperature? So go ahead, take a few moments, figure that out, and hit pause so that you could figure it out until you have the answer. Now the second question is what is the SI prefix for milli? What values is assigned for that SI prefix? So Figure out what value means. It could be exponential or the real long written out number in decimal value. Okay, so take a moment, hit pause, and figure out the answer. And then number 3, 58.0 milligrams is equal to some value in kilograms. If you notice that this equation has the equal sign, this equal sign means that the value on the left of the equation, or the equal sign, is going to be equal to the value on the right of the equal sign. So essentially what you have is a small measurement of some mass, 58.0 milligrams. You have to make it so that it has the same value, the same amount of stuff in terms of a kilogram. It's kind of like saying, well, I have a 4.5 pounds of apples. How many ounces is that? That's essentially the same thing, but using metric units instead. So how we'll have to do that is we'll have to move decimal values. So of course I'm going to verbally explain this to you. Milli has a value, exponential value of 10 to the negative 3. Kilo has an exponential value of 10 to the positive 3. So the difference between negative 3 in milli and the difference in kilo is a total of 6 decimal values. Now, knowing that milligrams is a smaller unit than kilograms, and that we have to make sure that the equation is equal, milligram is a smaller unit, kilogram is a larger unit, which means that when we move the decimal point forward to 58.0, we're physically going to move this decimal point right here to the left by 6 times, because milli is 10 to the negative 3, kilo is 10 to the positive 3. There's a difference of 6 decimal values with 6 times 10. Well, basically move the decimal 6 times, which is like a million times. So the number in front of kilo has to be 1 million times smaller than 58.0, which means that you move the decimal point 6 times over to the left. So the answer for this will be 0.000040580 kilograms. Same thing with seconds. Seconds has a value of 10 to the 0 power because it has a value of 1. Okay, 10 to the 0. Nano is 10 to the negative 9. So essentially you'll be moving the decimal values a total of 9 times. Seconds being a larger unit than nanoseconds, because nano is a really small value. So you'll be moving this decimal value to the right because you have to make a balance. Okay, so 0.07, it'll be moving to the right by a total of 9 times. So you have 7 with 7 zeros at the end. Okay, and that's basically the practice problems for this page. And that is the end of this PowerPoint. So I'm hoping that you will be able to listen to this. If you have any confusions, any questions, you can re-listen to this PowerPoint and try to figure that part out. And if you have any questions, ask in class the very next day.